We move through it. We live inside it. We assume it's always been there, infinite, silent, invisible. But pause for a moment. What actually is space? Not metaphorically, not as a setting or background, but as a thing in itself. Is space a substance? A field? A dimension? A relationship? Or is it just an illusion? A mental grid we impose to make sense of motion and distance. To understand this, we need to travel back through history and forward into the mysteries of modern physics. For centuries, space was the stage on which the universe performed. Newton imagined it as a vast, unchanging container, an infinite backdrop that existed regardless of whether anything was inside it. Space was absolute, fixed, and eternal. If you removed all matter, if you took away stars, planets, and galaxies, space itself would remain. It was an invisible, silent, and immutable expanse. This view was reassuring. It made the cosmos feel stable, logical, and comprehensible. Space could be measured, mapped, and navigated. It was the framework that allowed us to calculate motion, forces, and trajectories. But then, Albert Einstein changed everything. His special theory of relativity, published in 1905, introduced the idea that space and time are linked in a single entity called spacetime. This was no longer a static container. Instead, space could stretch, compress, and bend. By 1915, with general relativity, Einstein showed that gravity was not a force pulling objects across a void, but the effect of mass and energy curving the fabric of spacetime. Massive objects, like the sun, warp the geometry around them, causing planets to orbit not because they are tugged by invisible forces, but because they follow curved paths in a curved space. This warped spacetime can ripple in waves, collapse in black holes, and even expand, stretching the universe itself. Space was no longer a passive backdrop. It was dynamic, active, and intertwined with time. In this view, space became a physical entity with properties capable of influencing and being influenced. Space had agency. Yet, despite all this transformation, space remained real. It was measurable, observable, and fundamental. But is this the end of the story? To understand whether space is fundamental, we need to dive deeper, down to the very fabric of reality, at scales smaller than atoms, smaller even than particles. This is the realm of quantum mechanics, a world where the rules of classical physics no longer apply, and where space itself becomes ambiguous. At the quantum scale, particles behave like waves. Their position is uncertain, described not by a point in space, but by a probability cloud. You cannot say exactly where a particle is, only where it's likely to be. Moreover, measuring a particle disturbs it. The very act of observing forces it to choose a position, collapsing a range of possibilities into a single outcome. This uncertainty is not just about particles, it's about space itself. If positions are fuzzy, then the very concept of a fixed spatial location becomes questionable. Even stranger is the phenomenon of quantum entanglement. Imagine two particles created together, then separated by vast distances, light years apart. Despite this, measuring one instantaneously determines the state of the other. They act as a single system, transcending the vast space between them. No signal passes, no information travels. The connection is instantaneous, defying our classical notion of distance and locality. Einstein called this spooky action at a distance, and it has been repeatedly confirmed by experiments. If distance doesn't affect these quantum links, then what does space mean? Could it be that space is not fundamental, but a convenient description of how objects appear related? The very idea shakes the foundation of how we understand reality. This leads us to an astonishing possibility. Space is not fundamental, but emergent. Much like how temperature emerges from the collective motion of countless molecules, space might arise from a deeper, more abstract foundation. Some physicists propose that space emerges from networks of quantum entanglement. The geometry of space could be a reflection of the pattern of connections between the fundamental building blocks of reality.
This idea is central in modern attempts to reconcile quantum mechanics with gravity, the holy grail of physics. One compelling clue comes from black hole physics. Black holes have entropy, a measure of disorder or information. Surprisingly, this entropy scales not with the volume inside the black hole, but with the surface area of its event horizon. This suggests that all the information about the interior is encoded on the boundary. This is the essence of the holographic principle. Our three-dimensional universe might be a kind of projection from information stored on a two-dimensional surface. Space, then, could be like a hologram, an illusion of depth created by a more fundamental layer of information. Another radical proposal is the ER equals EPR conjecture, which suggests that quantum entanglement, EPR, and wormholes, Einstein-Rosen bridges, ER, are two sides of the same coin. This implies that entangled particles are connected by tiny tunnels through spacetime. If true, then the connectivity of spacetime itself arises from entanglement. More generally, space might be best described as a vast network, a web of information and relations, rather than a continuous expanse. This shift in perspective is profound. It suggests that what we experience as distance is actually a measure of the strength or nature of underlying connections. So, if space is emergent, then what exists outside space? What is the deeper reality from which space springs? If space is not fundamental, then the foundation of reality lies in something more abstract and mysterious. Many theorists suggest this foundation is information itself, pure abstract bits and qubits, relationships and interactions. In this view, reality is a grand computation or a web of quantum correlations. Some even propose that time itself is emergent, a macroscopic consequence of more fundamental, timeless laws. This challenges our deepest intuitions. We think in terms of objects occupying places and moments, but these may be emergent patterns, not fundamental features. Moreover, our consciousness might be tied intimately to these patterns. After all, we never experience space directly. Our brain reconstructs a spatial model from sensory inputs. Some interpretations of quantum theory, like participatory realism or cubism, suggest that the observer participates in shaping reality. Observation isn't passive, it's a creative act. If space emerges from entanglement in information and consciousness participates in reality's unfolding, perhaps the boundary between mind and space blurs. Is space then a kind of interface, a shared arena shaped both by the underlying quantum structure and by conscious observers? This raises profound philosophical questions. Is reality independent of space? Can something exist without spatial extension? What does it mean to be outside space? From a physical perspective, theories like loop quantum gravity, string theory, and holography are beginning to explore these ideas, but the final answer remains elusive. What we do know is that space, once considered the ultimate arena of existence, is now understood as a complex, possibly emergent feature of the cosmos, and that suggests the possibility of a reality outside space, one that underpins and gives rise to everything we see. So, is there reality outside space? The answer is likely yes. Space might not be the fundamental container of all things. Instead, it may be a magnificent illusion, a stage built from more primal elements, quantum information, entanglement, and relationships. If so, what lies beyond space is the true fabric of reality, a realm stranger than anything our senses or classical physics can reveal. The challenge now is to discover that realm, to peer beneath space's shimmering veil and glimpse the ultimate source of existence. As we look up at the stars or down at the particles beneath our feet, we must remember the universe might be far richer, deeper, and more mysterious than space itself, and that the reality outside space, if it exists, is the most profound mystery awaiting us.